Welcome, Calculus BC. This is lesson 3.1, concavity, points of inflection, and second derivative test. Let's go. So concavity is about either doing shapes that look like this or shapes that look like this. It's like a cave type shape. And you have like concave upward is when it looks kind of like a cup, kind of pushing up. And then concave downward is when it's going down. Or you can also think of it like a smiley face. Smiling is happy for concave upward, and it's sad for concave down. So this is a graph of this, and this definition talks about tangent lines below the graph, blah, blah, blah. But the big thing you need to know, for concave downward, the second derivative is positive. So f double prime is positive for concave upward. Concave downward, the second derivative is less than or equal to 0, which means the second derivative, f double prime, is negative. That's the difference whenever you're looking at that analytically. So let's look at the graph of x cubed, and we'll talk about points of inflection. Points of inflection are where the concavity changes in a function. So in this case, we have a point of inflection at the point 0, 0. This is the graph of y equals x cubed. How to find a point of inflection? These exist when the graph has a tangent line at that point and the graph changes concavity. So both things have to happen. Analytically, how does this work? Well, points of inflection are where the second derivative equals 0. So it's kind of like critical numbers, but for concavity. So if I were to do this analytically on this graph, I know my point of inflection is here, and I could even look at this graph and I realize the left-hand side is concave down because it's kind of doing this sad face shape like that. If I like filled in the parabola, where it's concave down, on the right side we're going to be concave up. Because if you filled in this shape, it's kind of like doing this. So it's concave upward. So yeah, sometimes you just kind of like gotta like just do this with your hands to kind of look. Is it concave up or down? Sometimes it is hard to interpret that on a graph. Now if I were to do this analytically, so to prove that that's a point of inflection, this is what I would do. I would do the second derivative. So the first derivative is 3x squared, and then second derivative is going to be 6x. Well, to figure out where potential points of inflection, set the second derivative equal to 0, and then you say, oh, x equals 0 is a point of inflection. But we have to prove that it changes. So I'm going to do this table where it's kind of like we did with the first derivative test. And then we're going to check to left and right. So I'm going to try a test point where x equals 1, and then x equals negative 1. We're going to plug that into the second derivative this time. If you plug it into the second derivative, 6x, you get 6 times negative 1 is negative 6, which is negative. And then you plug it into the x equals 1, so you're going to get 6 times positive 1, which is positive 6, which is positive. So we are concave down over here and concave up over here, so x equals 0 must be a point of inflection. And that's reflected in this graph right here. Moving on from there, let's take this example of a graph. So we got this thing going. Notice it's curving. Notice this part's straight, and this part is also straight. So on which intervals is the graph concave upward? I think from here to here looks concave upward, -2 to 1, or -1. This interval also looks concave upward, so from 1 to 3. And this interval right here from 4 to 5, because you could do that, is concave upward. And that's going to be it. Concave downward, which intervals are downward? So it's going to be this area right here, so from -1 to +1. And that's straight, that doesn't count. And this is concave downward, so from 5 to 6. So that'll be my last interval. Now, which intervals the graph have no concavity? That's like a straight line, you can't tell. So it's going to be, let's do that in a different color. Let's do that in green. That's going to be from here to here. So that's going to be from 3 to 4. And also on this straight part right here, from 6 to 7. So those are my intervals. Where the points of inflection, remember it has to have a tangent line and it must change concavity. So right here is a good one. So x equals -1 is a potential spot. Where else? Right, because it's going from down, concave up to down. Right here is also a point of inflection, so +1. Now, right here we go from concave up to no concavity. That doesn't work. And also, since this is kind of like a piecewise function, because that's a linear function, and this is a polynomial function. So this isn't, there's no tangent line here. This is one of those sharp turns in a way. Same thing up here. This is also going to be sharp turn. So those points don't work. Right here would work, so I'm going to include positive 5. Now 6, again, sharp turn, so no good. And nothing along there. So we have 3 points of inflection on that graph. Determine the points of inflection on this example. So if I'm doing this without a graph, I'm going to do the first derivative, which is going to be 4x cubed plus 3x squared minus 6x. And then I have to do this second derivative. So the first thing you do when determine points of inflection, find your second derivative. 12x squared plus 6x minus 6. And you're going to set that derivative equal to 0. Points of inflection are 0. Yeah, just 0. So let's think of it as does not exist. No, that doesn't make sense. Just 0. So that's going to be 12x squared plus 6x minus 6. Divide everything by 6 because you can. So you get 0 equals 2x squared plus x minus 1. And this is where you have to solve either quadratic formula or factoring. Now I don't care how you do this, but like multiplying those two to negative 2, the middle is going to be a 1. So the two numbers that multiply this, add to this, are positive 2 and negative 1. So my factors is going to be 2x plus 2 times 2x minus 1, but this can be reduced. And you might do this differently, I don't care. This is how I learned to do it. At this point, your calculus, you can do it your way. So my solutions are x equals negative 1 and x equals positive 1/2. Now, I want to, those are potential points of inflection. They're kind of like critical numbers. But we have to check that they actually change concavity. So we're going to plug those in, do a table again, and so we'll test values. I'll go negative 2, 0, and positive 1. Those are good test values. So if you plug in 2, now second derivative, I'm going to use this reduced form of the function. I think that'll be easier, but you could also use this one. So if you plug in negative 2, I'd get 2 times 4 is 8, minus 2 minus 1, which would be 5, which is positive. If you plug in 0, you'd get negative 1, which is negative. And if you plugged in 1, you'd get 2 plus 1 minus 1, which is 2, which is positive. So my concavity is concave up. We have discussed the concavity too. So my points of inflection, we are concave up here, concave down here, and concave up. So my points of inflection happen when x equals negative 1 and positive 1/2 because it changes concavity. And we're concave up on the interval, this one and this one. So I will say from negative infinity to negative 1 and from 1 to infinity. And we're concave down on the interval in between, which is negative 1 to positive 1/2. There you go. All right, second derivative test, use that to find a relative min and max. So sometimes we want to find relative mins and maxes. We've done first derivative, and you can use that. But second derivative is sometimes another way to do this, and sometimes I find it easier. So the procedure is find the critical numbers, and so that's with the first derivative test, equals to 0 or does not exist, derivative for that. And then you want to plug those critical numbers in the second derivative. So instead of plugging it and making the table, you plug it in a second derivative. If second is positive and it's a critical number, you have a relative minimum because you're concave up and it's a critical number, it must be a minimum. If it's negative, that means you're concave down. You must have a relative max because it's got to be like at the top. And if it's 0, second derivative test is inconclusive, so you have to go back to first derivative. So what are the benefits of using this test? Well, if it's easy to find the second derivative, I like the second derivative test because I hate doing the tables. But the downside is this doesn't always work. And if the second derivative is annoying to figure out, then it's maybe just do the first derivative test. But it's up to you. Sometimes I like doing this one. So even, let's go back to this example. Sometimes it's, if I wanted to prove, well, this doesn't, no, this one doesn't have any critical relative mins and maxes. So let's do this test example. So it's especially easy on polynomial functions, I think, because it's easy to find second derivative. So you can do the first derivative, figure out your critical numbers. So it'll be negative 12x cubed plus 12x. Set that equal to 0. You're going to factor out 12x. It's Let's get negative x cubed plus 1, negative x squared plus 1. So your critical numbers are x equals 0 from this term, and then positive and negative 1 from this term. So you got 3 critical numbers. So we got to figure out relative mins and maxes. I'm going to use second derivative because it's very easy for me to derive this. So f double prime of x is going to be negative 36x squared plus 12. And so I'm going to test each of these. So I'll make a little table here. 0, negative 1, 1. And what is the second derivative going to be? Well, if you plug in 0, it's going to be 12. If you plug in negative 1, you will get negative 24. If you plug in positive 1, you get negative 24. Since this is positive for x equals 1, we have a relative, we said positive is concave up. So I can say there's a relative minimum at x equals 0. And there's a relative max at the other two because it's negative, so it's concave down for each of those, at x equals 1 and negative 1. So yeah, that's easier for me. Otherwise you could have done a bunch of tables, first derivative, I don't care. And we're done.